All right, so moving to some foundational concepts in computational medicine. So basically, we have NLP and deep learning models. So we'll be discussing that. First, we'll be discussing transformer architecture. So for that, we will first talk about self-attention, and in self-attention, we will be basically discussing about query, key, and value, and how it captures word relationships in sequence. Right. Then we'll talk about masked attention, then positional encoding, and dropout. Right. So let me just go over this part. So NLP and deep learning, we first have transformer architecture and attention mechanisms. So transformer architecture is discussed as a sorry, superior method for modeling context compared to older approaches like the word to vec. So first we'll discuss self-attention, which is a mechanism that allows each element in a sequence to focus on different elements within the same sequence, with the weights of this focus being determined dynamically by the content of the elements. For example, in the sentence, the cat sat on the mat, the word cat might pay more attention to mat. The formula for calculating self-attention is noted to have complexity of n square. So we have key components Q, K, and V, right? Q means the query. It represents the information used to attend to the relevant parts of the sequence, right? Then we have the key, which represents the information used to determine the importance of different parts of the sequence. Then we have V, which is the value. It represents the actual content or information for each position. These Q, K, and V matrices are essential components of transformers, enabling the model to capture dependencies and relationships. Multi-head attention is basically involving multi-parallel attention layers, right? So context modeling superiority. First, we'll talk about the differences between transformer architecture and word-to-vec architecture. So transformer basically employs a self-attention mechanism for dynamic context modeling, while word-to-vec represents words by a fixed size vector and does not capture dynamic content. So transformer captures long-range dependencies by assigning different weights to different sequence positions, while word-to-vec considers only a fixed window of words around the target word. Then transformer incorporates positional information through positional encodings, while word2vec doesn't use or encode positional information inherently. Also, transformer architecture inherently captures the bidirectional context, while word2vec only considers context words before the target word, limiting its ability to capture bidirectional relationships. Also, positional encoding is achieved by adding a fixed vector calculated based on the position of the token in the sequence to the original word embeddings. Now, masked attention used during the training of transformer models. Masked attention ensures that the model cannot access future tokens when predicting the next word, preventing positions after the current position from being attended to. Then we have dropout. This is a regularization technique applied to the sums of embeddings and positional encodings in both the encoder and decoder stacks of the transformer model. Word embeddings. The pre-trained word embedding model, GloVe, uses the word as the atomic unit for representation. Challenges of one-hot encoding are, while used to represent categorical data as binary vectors, one-hot encoding for text has significant challenges. It results in high dimensionality, which can cause overfitting, creates sparse data matrices, and suffers from a lack of semantic information as it treats each word independently and ignores relationships between them. So the sources place these NLP and deep learning concepts directly within the context of healthcare and medicine, particularly concerning the specialized models and knowledge representation. So now some specialized deep learning models, we'll be talking about that. We have BERT, that is bidirectional encoder representations from transformers. So some examples for special DL models are BioBERT, Clinical BERT, and DNA BERT. So the general BERT architecture is used for tasks involving text undergoing pre-training, for example, MassLM, and subsequent fine-tuning for specific downstream applications like MNLI, SQUAD, and NER, that is named entity recognition. So named entity recognition is relevant for extracting crucial information from text, for instance, identifying Louvre Museum or Paris as named entities in a sentence. Then we have knowledge representation and decision support systems. So NLP models often interact with structured knowledge to provide utility in healthcare, emphasizing the role of ontologies and interoperability. Then biomedical ontologies, which formally represent the concepts, entities, and relationships with biomedical knowledge. They consist of classes, concepts, relationships, and associated attributes. Role in decision supported systems, DSS, ontologies are critical for building DSS because they offer a standardized way to represent these medical medical knowledge, ensuring that terms and relationships are consistently understood across different systems. Right. Moving on, interoperability. The shift in healthcare data exchange towards fast healthcare interoperability resources is noted. So FHIR is basically resource centric, that is, it is granular and utilizes modern formats like JSON or XML objects and RESTful APIs, making it developer friendly, and it facilitates collaboration and information sharing between different healthcare systems. Right. Now, since we have talked about what exactly that the whole uh, transformer architecture was in brief, we'll be diving deep into self-attention. Okay, so let us see that. So self-attention, which is a mechanism that defines how a sequence element interacts with other elements within the same sequence, right? We've already covered all these things, so we'll move on. The formula is this. So these Q, K, and V matrices are essential components of self-attention mechanism in transformers, enabling it to effectively capture dependencies and relationships within input sequence. And the formula is attention is softmax Q times K transpose upon root of dk, and outside we have multiplication with V. So the incorporation of self-attention is the key reason that the transformer architecture is considered superior to older language processing models like Word2Vec when modeling context, because it has dynamic context modeling. So the transformer uses self-attention to achieve dynamic context modeling of sequence words. This contrasts with Word2Vec, which represents words using a fixed size vector and does not capture the dynamic context of the word. Then long range dependencies. Self-attention also allows the transformer to capture longer range dependencies. It achieves this by assigning different weights to different positions in a sequence, an ability lacking in Word2Vec, which only considers a fixed window of words around the target word. Also, bidirectional context. They inherently capture bidirectional context, whereas previous models like Word2Vec often limit context to words only preceding the target word. Right. Now, also we have terms like masked attention and positional encoding. So first, let's discuss masked attention. This variant is specifically used during the training of transformer models. Its purpose is to ensure that the model cannot access future tokens, positions after the current position, which is crucial for language modeling tasks such as predicting the next word in a sentence without knowing the next word and only knowing the preceding words, where a word should only attend to preceding words. And we have positional encoding, which basically adds a fixed vector to the original word embeddings, right? Now let's discuss positional encoding, all right, since we didn't get exact implementation here, right? So necessity and function of positional encoding we'll be discussing. First, it is basically a crucial technique required by the transformer model due to nature of its core mechanism, that is self-attention. So the self-attention mechanism does not inherently encode positional information. If the input words were only represented by their fixed embeddings, the model would lose all its information about the order of words in the sequence. So when we inject positional information, we basically are injecting information about the position of words or tokens in a sequence, the position or the indices. It is designed to supplement the word embeddings with details about the token's position or the location in the sequence, right? So the ability of transformer architecture to incorporate positional information through positional encodings is cited as one of the key differences that makes it context modeling superior to the word-to-vec architecture. So basically, we have the integration method. The most common approach is to add a fixed vector to the original word embeddings, and we have formulas. So basically, positional embedding pos comma 2i is sine of pos upon 10,000 to the power 2i upon d model, right? And similarly, position comma 2i plus 1, that is odd index, uses cos position upon 10,000 to the power I upon d model. So these formulas indicate that the sine function is used for even indices 2i, and for the odd indices we have the cos function, right? And d is the dimension. Now that's what exactly we got to know about positional encoding. Now after that we'll be discussing about dropout, right? So dropout is basically a regularization technique applied in transformer model to prevent overfitting and improve the generalization. So the source that we have used here, it states that dropout is applied in relation to both the embedding layer outputs and the output of the subsequent sublayers. So dropout is specifically applied to the sums of embeddings and positional encodings in both the encoder and the decoder stacks of the transformer model. Dropout is also applied to the output of each sublayer, right? It is done before being added to the sublayer and normalized. Is not true. This is the statement that is not true regarding application of dropout, right? So dropout is applied to the combination of word embeddings and positional encodings and applied to the output of each sublayer, right? So that's all about today's video.